With that, I think I want to transition to our last session for today. The presenter for this one is Lei Li, Assistant Professor from UCSB Department of Computer Science. And Lei Li is going to be discussing around high performance training and inference with the focus on NLP. With that, let me welcome Lei Li for his talk.
Render you. There you go.
Hi, everyone. Very glad to share my work recently on high performance training and the inference for NLP models on GPU. Okay, so we know that these large neural networks are pushing the boundaries of AI, in particular for applications like machine translation, automatic speech recognition, and visual recognition. Recently, all these applications are really relying on this large-scale neural network. In particular, one neural network very useful for all these applications is called transformer models. Right now, it's the transformer models are reaching the state-of-the-art result for all these applications, in particular for machine translation, language understanding, image classification, and speech. So these models, like what I described on the left part, these are the common architecture. They can vary in different number of layers and the different number of parameters. Normally, the basic version include around 50 to 100 millions of parameters already. That's pretty big number. And if you train that on single GPU, that requires a few hundred hours of GPU time to train that. And more latest work using this type of a transformer model, they are relying on very large model. Here I plot the model size versus training time. In particular, swing transformer here is the latest transformer model for computer vision for image classification. It gets the state-of-the-art result and for last year, and it's actually the best paper from ICCD last year. And RASP is getting the best result right now for multilingual machine translation. And the largest one is this GPT-3. Perhaps you have heard of this. This is a language model with over close to 500 billion parameters. And you need millions of GPU hours to even train that model. So where if you compare that with compare the energy needed to train the model, it's equivalent to driving a common passenger car for 146 years. So that's a lot of energy consumption. Now, of course, that's very expensive. And at the university, it's very difficult to do that as well. So one of my focus is to develop high performance library for this specific type of transformer model family. So we developed this library called LightSeq. It's an efficient training and inference library comparing to some baseline framework like TensorFlow, PyTorch. So both are popular deep learning frameworks. You can get 14 times the speed up in inference and 45 to 250 times the speed up, speed up compared to PyTorch and TensorFlow. It's also very convenient. You can still use TensorFlow, PyTorch, or Hugging Face, etc., to describe the model and use port that model to LightSeq, and then use LightSeq to further train and inference. It's also deployed in industry scale products. It's already deployed in VolcTrans, which is serving one of the clients of VolcTrans is TikTok. It's serving 1 billion customers every day. Well, in comparison, I'm listing several libraries for transformer computation. Includes one library from NVIDIA, faster transformer, and from Tencent, turbo transformer, and from Microsoft, DeepSpeed. They are designed for all different kind of purpose. Faster transformer and turbo transformer are really used for inference. They support both a BERT, GPT type of model, and full transformer as well, but they do not support more advanced model like VAE or multilingual transformer and with more diverse inference techniques. DeepSpeed instead, it's focused on training. It doesn't really support any particular inference method. So our LightSeq in comparison, it supports all different types of model and all these various inference technique and supports training as well. It can integrate with PyTorch and TensorFlow as well. So in terms of performance, we compare this LightSeq with several other frameworks on different model size. We have 6 encoders, 6 layers of encoder, 6 layers of decoder. That's a standard transformer. We have larger ones like a 12 encoder, 12 decoder, and even larger one with 24 encoder and 24 decoders on different types of GPUs, 300 and 800 as well. So this is the training performance in terms of the number of tokens per second. And in comparison, if we so this is the same plot, but we plot it in terms of speed up comparing to the basic PyTorch. So with FairSeq is a PyTorch library specifically designed for the sequence learning. If you combine with FairSeq with the Apex library, which is again developed by NVIDIA for quantization, it can achieve some a little bit speed up. But if you combine FairSeq with LightSeq together, you can achieve almost 3 times the speed up in terms of training. So in terms of inference, we also compared inference of this transformer model. This is a machine translation application on T4 and P4 GPUs. Usually we don't really need those 800 or B100 those powerful GPUs for inference. So we can use less powerful GPUs like T4. So in both cases, the LightSeq achieves over 10 times the speed up compared to PyTorch and TensorFlow. It's also faster than the faster transformer library from NVIDIA. So there are 3 major techniques that's very important for the LightSeq improvement. They are the kernel operation fusion and dynamic memory management on GPU and the optimizer acceleration. So in the computation of transformer, there are 2 types of the computation. There are matrix multiplication, which can be realized by native library of CUDA library or cuBLAS. And there are the rest operations. So that one technique we used is to fuse all the rest operations together, all the operations other than the matrix multiplication, and fuse them into just one operation. And then also we optimize the number of times we need to do the reduce operation by using algorithmic reformulation. So with that, we can basically improve the portion needed for operations other than matrix multiplication. You can see comparing to the baseline and the light-seq approach, after optimization, the matrix multiplication occupies the majority of the time here. And we can also improve the memory usage as well by dynamic memory management. So comparing to the basic PyTorch implementation, where we can reduce the memory consumption by almost half, then we can, with that reduction, we can increase the batch size for transformer training. And with that increased batch size, not only we can improve the speed for training, but also we improve the accuracy as well, because usually this large batch size will stabilize training and also improve the performance. So looking forward, right now we still use handwritten optimization library, but in order to tailor to different hardware, as Professor Ding mentioned, in looking to future, we still need to do adaptation or automatic compilation to different hardware and auto-tuning according to the different data distribution. And I haven't talked about the very large models. So far, we can only optimize for kernels on single GPU. We still need to optimize the training and the inference for very large models that cannot fit on a single GPU. So with that, I'd like to take questions.
Thank you so much. I think I don't see any questions on the chat tool. Maybe I'll just pause for another second and see if there's any new questions coming in. No, perhaps folks are getting hungry. I think in terms of, thank you so much for your presentation, and hopefully we'll discuss more of this as we get into the panel session that's just starting now. That concludes actually all the sessions. So maybe I just want to once again thank all the speakers and session presenters. They're all very busy, and I want to thank them all for their time and effort in terms of discussing their various perspectives today.